Okay, I'll just briefly review what I started off with last time, or actually we went quite a bit through this, and then I had to stop, so let me change this pen, it's not working properly. Thermionic emission and vacuum tube devices. And there is familiarity on this topic, so just a quick word from what we did last time. You see, if the electron has got within the crystal, it has got enough energy, more than the work function, it can come out of the crystal if there's enough of thermal vibrations, right, if you get enough energy for it. But what I mentioned the last time was that unfortunately, as it comes out, it sort of leaves behind a positive charged, effectively positively charged area. So there's some self-limiting condition. After some time, no more electrons will come out because there's now positive charge. They'll simply be sucked back. To make use of in a real device, what we did was to enclose the whole thing in a vacuum. And then between the cathode and the anode, we apply a voltage. Okay. And in addition, what we did was provided a separate heat source to heat up the cathode, and so electrons come out from here into a vacuum sealed envelope. Okay? This is what is known as thermionic emission. As you heat it up, the electrons get enough energy to go over the potential barrier that is created by the work function, and so they are emitted. And then we went on to look at how to derive the current density in such a case, and the equation is known as the Richardson-Dushman equation. Is the text clear or is it too light? Tell me if it is too light, I'll change a pen. You can see it? Okay. And so what we had obtained the last time was that the current density for the electrons that are coming out is going to be given by this equation where there is an exponential dependence of the negative of 1 by t, where B naught was known as the Richardson-Dushman constant and had a value equal to 4 pi e me k square. I'm not going to repeat the whole thing, just as a quick brushing through of this, and which turns out to be 1.20 into 10 to the power 6 amps per meter square per Kelvin square. All right, amps per meter square per Kelvin square. And I pointed it out that it's an easy one to remember. If you think of it in terms of centimeter square, it turns out to be simply 120 amps per centimeter square per Kelvin. So that's a common number you'll find in problems and things. I had given Richardson constant. They may usually just refer to it as Richardson constant. In other books as Richardson-Dushman constant is 120 amps per centimeter square per Kelvin squared. So this is one equation we have for the current density in such a device due to thermionic emission. But I did point out that there is a modification that we have to make of this situation, and that is related to the fact that in quantum mechanical consideration there is a finite probability that when an electron encounters a barrier, it can get reflected back. Okay, it can get transmitted and it can get reflected back. So what we did was to introduce something called a reflection coefficient. It's like a wave if you treat it. And this reflection coefficient is the probability that it will get reflected if reflection coefficient is large, namely for very large barriers, barriers tending to infinity, the probability that the wave will be reflected back is higher, and so on. So then we modify our equation of this Richardson-Dushman equation suitably to take into account this idea. And so then we have an effective current density. The constant has been modified suitably, t squared exponential minus phi by kt. So this BE accounts for the fact that there is a finite probability of reflection. This is what I had said. And what is BE? It's related to the previous Richardson constant by 1 minus r B naught. Okay? So what this simply tells us is if r is 0, then it is simply reducing to the previous equation of the Richardson-Dushman equation. If the probability that it will be reflected is high, then accordingly the current density of the electrons that are flowing through or overcoming the barrier is low. The current density decreases as R increases. Typically, it is seen that BE is equal to about half B naught for most metals. This is just a quick glance through what we did the last time. Okay, so there is some finite probability for the reflection in the case of many metals, and so we have BE is equal to half B naught. For certain oxides, we find that it is actually 1 into 10 to the power 2 amps per meter square per Kelvin square. These are particularly oxides that are used in coating filaments and things like that, that are used for such kind of emission. So we got the idea that the current that is going, current density is related to the work function and it is related to temperature. So ways in changing the current density would be either change the metal that I'm using altogether, or I can change the temperature. I increase the temperature, I will have a higher current density flowing through it. Now we're going to take into account one more effect, and that is that when we apply a voltage to a device like this, so when I am making the anode positively biased here, I also affect the emission of electrons by means of the field that is created between these two. It is not simply serving here to catch all the electrons that are coming out, but it actually influences the field that the barrier that the electrons see in coming out. In other words, my barrier phi, which they see, is affected in some way by the presence of the bias there. So that effect is known as the Schottky effect. And it turns out that it enhances the emission by lowering the barrier. So instead of having phi, now we have a barrier that is phi effective, a lower barrier than the barrier in the absence of a field. So the application of that voltage produces the barrier. Consider an electron just outside the surface of the metal, and we are going to look at what are the forces that are acting, what are the barriers that it sees. All right? When the electron has gone out of the metal, there is what is called an image force, as if there is an apparently positively charged region that is pulling back on it. And then in addition to that, we have the applied bias here applied to the anode. Okay? So, and then you have that the thermal excitation is also there for the electron to go out. So these are the different forces that are acting on this electron. This attractive image force, as it is called, do you understand? It's an apparently, when an electron is gone, it's left behind an apparent positive charge. The image force can be modeled using PE of the image force as a function of x. Simply it's electrostatic attraction, and so we will get a 1 by x dependence, minus 1 by x dependence, minus indicating it's the attractive, where epsilon naught is the permittivity of free space. In this equation, the reference level what we have used is PE is equal to 0 at x is equal to infinity. As you go farther and farther away, that attractive force is not there. So at x is equal to infinity, PE is equal to 0. But what we did earlier was to define our PE is equal to 0 inside the metal. If you recollect, we said that inside the metal, the potential energy is 0. So we have to sort of reconcile these two references by altering the equation suitably to take into account our earlier assumption that PE is equal to 0. So if we change our reference level, then the equation for PE for the image force is modified as EF plus phi minus E squared by 16 pi epsilon naught x. That means even at x is equal to 0, it sees this barrier EF plus phi. That's my reference level. So with respect to that, I have this attractive force. So at large x also, I'm sorry, not at x is equal to, at large x, we still have this regular barrier EF plus phi. As x increases, this term decreases. So at large x, we have the same barrier as we had before. That means what we have done is change the equation to our reference level of potential energy is equal to 0 within the metal. That's what we have done by rearranging it in these terms. At large x, the potential energy that the electron sees is still simply EF plus phi as we had before. It is only in the short range that this term, the attractive force, is modifying the whole effect. So let's make a plot of these different things and see what we get. We're going to plot energy versus x, and the image force then is something like this. As x is small, in that equation there is a contribution. It reduces the barrier. But as we go farther and farther away, eventually at x large distances, we are left with the barrier EF plus phi. This is for the image force. On the other hand, we have the externally applied field, where we have the opposite, because it is now attracting the electrons out of it. So the field is opposite to that of the barrier that is being seen by the electron in trying to come out. So this is for the externally applied field as a function of x. Okay? I've got the image force that I've plotted, all right, which is simply that as we go to larger and larger x, it eventually reduces to EF plus phi. Okay, the image force lowering. I also have the effect of the anode, right, which is an externally applied field, which will give an opposite gradient, right? So I can now combine these two. This is attractive, right, in the negative direction. Now when I combine these two, I get something like this. I've got one force this way and one that rises to EF plus phi. And the combination of these two leaves me with an effective value in other words, initially this would have been the barrier in the absence of accounting for the image force. Once we account for the image force, we have effectively lowered the barrier by some amount, and now the actual barrier that the electron will see is EF plus phi. That is, the total P as a function of x is simply the combination of all this, EF plus phi minus E squared by 16 pi, which is the image force effect, and then minus Ex, the field, the applied field is. So the potential energy term is force E times the field times distance. And it is this combined equation that we have plotted here. Effect of the image force plus effect of the externally applied field. And what we are seeing is that now there is a barrier that is no longer given by phi, EF plus phi, but it is EF plus phi effective only. It is lower than before. And what is this phi effective? We call that the effective work function. And so phi effective may be written in terms of phi as phi minus square root. Okay? We can get that from the previous equation, recombining it in terms, to write it simply in terms of one effective barrier, phi effective. So this effect is known as the Schottky effect. that is the application of the external field enhancing the emission that is coming out, because the barrier is lowered from phi to phi effective by this amount.
So what is EF in this?
What is?
EF.
The Fermi level. We've always used. So we are defining everything. Fermi level, the bottom of the band is 0. Fermi level is EF, and so my actual energy value is EF plus phi, right? So we are defining it in those terms, our energy value. So how does this modify the Richardson-Dürschmann equation? J is equal to BE T squared, just like before where we accounted for the reflection coefficient with BE. And then you have a modification coming within the exponent this time, minus phi minus beta S epsilon to the power half divided by KT, where beta S is known as the Schottky coefficient. We've just combined some terms together and has a value of E cubed by 4 pi epsilon naught square root. Okay? So the previous term, some of that was just combined together, and we've got it expressed as something into a field term, because the rest of it is simply a constant, E cubed by 4 pi. Excuse me. So this is now a value of 3.79 into 10 to the power minus 5 units are electron volts per volt per meter, square root of that. Where phi is expressed in electron volts units, and so now my combination of this will also be expressed in electron volts. So this is the third kind of equation that we've got, all for the same thing, basically modifications of Richardson-Dürschmann equation, taking into account firstly the possibility of reflection at the barrier, which is accounted for in this BE term, which is still 1 minus R B naught. And then the second equation relates to the possibility that the applied field causes a lowering in the barrier height, creating an effective barrier height. Now what happens when we go on increasing the field? As the field gets larger and larger, there's going to be some other effect that we are going to see. Okay, so no longer will it be purely thermionic emission. Energy supplied by the heat will not be the key thing anymore, but at extremely high fields, it's almost like the applied field sucks out the electrons. The application of the field is strong enough that you can actually suck out the electrons from it. And when we say high fields, we end up with the phenomenon of field emission. And what do I mean by high fields? Something of the order of 10 to the power 7 volts per centimeter. Okay, that's pretty high voltages, right? You're applying across a small tube device, if you imagine this much, say 1 centimeter, you're actually applying 10 million volts. So if you can do that, then you can have a phenomenon that is known as field emission, which does not depend so much on the temperature. So it becomes a temperature independent phenomena, whereas thermionic emission was directly related to temperature. So we'll look at this a little more. And what we are seeing effectively is, as before, we have our image force lowering curve is like this, except that now my field is very, very steep, the applied field. Earlier you may think of it as something that was more gradual voltage drop that is there, so the field is less. Here the field is high, and what I do is to create effectively the sum of these two, a barrier that's very, very narrow. You know, this goes up and then immediately this attractive force is there, so it sort of shoots down. And so the net effect is something like this. I create a very narrow barrier, which we'll call, say, xf is the width, if x is equal to 0 here. Okay, so this is at Fermi level. We create a very, very narrow barrier whose width is xf at the Fermi level. And now we are going to look at this barrier by approximating it by a simple rectangular barrier of width it's not the same shape, but it can be approximated by a very thin rectangular barrier of width xf. And when we have such a small barrier like this, there is a finite probability of tunneling. Remember, always we are looking at a classical picture, making modifications according to our understanding of the quantum mechanical behavior. So in other words, an electron sitting at the energy level EF, and the barrier there is XF, has got a finite probability of tunneling through this barrier and coming out here. It doesn't have to go over the barrier to get this side, it simply tunnels through. So over here we have now the following parameters. The height is as before, phi effective above EF, and the width is XF, X subscript F. And what we see is that the probability of tunneling is a function of both this barrier height and the barrier width. To express it simply, the probability of tunneling is proportional to, or is a function of, if you want to put, I just use the term F, of barrier height and barrier width. So in other words, of phi effective and of XF. In addition, the probability is also independent of temperature, because it's not going to go over it. So the probability of it going through will not depend upon the temperature. This is very different from the thermionic case, where temperature was the key factor there, though we got some lowering effects due to other phenomena there. But the primary driving force there was temperature. Here, temperature is not playing a role. We may express this approximately, the probability, as exponential minus 2 times 2 me phi effective to the power half xf by h bar. All right? It's a function, I said, simply, without giving you any relation, just to appreciate the terms that are involved there. The height of the barrier, the effective function, the width of the barrier, and those terms are all now approximately related in this manner. Now we want to know what is xf. How do we define what is xf? And if we look back at the figure, we will see that the width of the barrier, when x is equal to xf, at that point the energy term is how much? EF. So if I substitute into the equation for energy, the total equation that I have, namely, which we wrote earlier, potential energy as a function of x is equal to EF plus phi minus E squared by 16 pi epsilon naught x minus Ex and the field. This was the equation that we had. In this case, what we know is that when x is equal to xf, the energy term is, that's how we define the xf, that at Fermi level, what is the width of the barrier. So by making the substitution as x is equal to xf, we can then calculate what is, and here we have EF is equal to this term, right? At very large fields, the second term may be neglected with respect to the third term. This term is a very dominant term at large fields. So I can rewrite this equation as EF is equal to EF plus phi minus E xf and the field. That is, neglecting this term, because this term becomes the dominant term. So neglecting the second term with respect to the third term, we substitute for xf, and we know that the energy barrier there is EF, by definition, how we had defined the whole thing. And so you can solve this then for phi first, or for xf, and we can write then that xf is equal to phi by E epsilon. These cancel out. So I've got a relationship for xf in terms of the field as well as in terms of phi, which I can now go back and substitute into this equation. And so now we write that the probability of tunneling through is now exponential minus 2 times 2me phi effective raised to the power half, and we are making the substitution for xf as phi by E times the field. So we will write phi by E times the field, and then you had the h bar term there. So we simply substituted for xf in terms of phi and the applied field. You will note that the variable there is simply the field, not phi. Phi for a particular metal is constant. So everything else there is really constant except for this term. And that's why the whole thing is called field emission. I make this stronger, the probability of tunneling through is higher because of this exponential minus term. Right? So that is why it is referred to as field emission. Now, to make a more rigorous calculation, we should include a few other things, which we are not going to do. We made some simplification. So, first of all, our barrier is not rectangular, strictly speaking, though we approximated it by a rectangular barrier. So, any more accurate calculation should account for the shape of the barrier and not simply use the simplification of a rectangular barrier. Secondly, there are electrons below EF that can tunnel through. Right? We looked at EF, at energy EF, the electron tunneling through. But we've got lots of electrons below that also which can tunnel through. Now, when we account for the fact that the barrier is not strictly rectangular but is more like this shape, then the probability of the electrons tunneling that are below EF, depending on this width, we can say that it's lower. Am I right? The electrons below EF also have a finite probability, albeit lower than the electrons sitting at EF. So we have to account for that also, that there are more than one. When I'm trying to calculate the current density, we don't simply say the electrons that are sitting simply at Fermi level, but close to it also there are the electrons that can go. So a more thorough calculation will take into account both these factors, and then we can arrive at an equation for the current density for field emission as B, some constant, epsilon square, the square of the field, exponential minus epsilon c by epsilon. Both B and epsilon c are temperature independent constants. However, they depend on phi. They are related to the work function phi. This equation, similar to what we had for the thermionic as Richardson-Dushman, is known as the Fowler-Nordheim equation. We can also use this equation when we are talking of tunneling not between simply into vacuum from a metal. This is the case that we considered where the electron was tunneling through, but the same equation can also be used for tunneling into the empty conduction bands of an insulator. There it is free to move around in the conduction band. So a similar equation can be used for tunneling from a metal into the empty conduction band of an insulator. The primary difference being that instead of the metal work function being considered here phi, our barrier will be phi b, which is the barrier height between the metal and the insulator. Work function that we looked at, the metal work function, is for emission into vacuum. So here the phi that we're talking of, for the phi b, the barrier, is really the barrier height between a metal and an insulator. That's what we'll have to consider in the equation. But otherwise, fundamentally, the approach is the same. Now note one other thing in this equation here. When you look at the Fowler-Nordheim equation, do you see a similarity with the Richardson-Dushman equation, which in its final modified form looked like this? J is equal to BE T squared exponential minus some barrier divided by KT. And you look at this here, B field squared exponential minus some kind of a constant divided by field. So in the case of the field emission, the field term is very much like the KT term. There it was T squared and KT was coming here. We've got now field squared and exponential minus 1 by the field term. So that's the primary difference. Here the field is what is providing all the energy for the emission. There, as I pointed out earlier, it is the temperature that is the critical factor. So where do we make use of this field emission is very interesting. I'll just point out a few things. One of the recent developments is what is known as field emission displays. That make use of this phenomena of field emission. We can enhance the emission by making the tip very sharp. Okay? So if the tip is very, very sharp, then the emission is enhanced. So for making a display, what they do is they put millions, literally, of such small tips on a surface and package it as part of a device. So we'll have the cathode here and an anode layer where there is some kind of phosphors that are coated. And when we apply the voltage, here there's not a, remember it's field emission, so very high voltage, and the gap between this can be kept very small so that the field is appropriately very high. And you have millions of these points, and when they emit electrons, they strike these phosphors and they produce light. So the viewer is on this side, our eye is here, and we are looking at a display where the light is produced by the emission of electrons from here and striking the anode that is coated by phosphors to produce appropriate colored light. Do you see the immediate contrast with the earlier vacuum tube that we looked at? In that, in its, I told you the vacuum tube display. Which one is it? The modern version of it, vacuum tube? Monitor, computer screen, and so on. Right? It fundamentally is a cathode ray tube, where we've got coating over here, and we are viewing from this side, and a beam of electrons that is thermionically emitted. We heat up the cathode, and we get a suitable deflection system, and we can create an image here. What is the primary difference between this and this field emission display? What's the big advantage? The second one is bulky, right? The monitor takes up so much of space of your whole computer device. That's probably the bulkiest part of a computer. So what they've come up with is now flat panel displays that are based on this field emission technology. There are other technologies for flat panel based on LCDs and things like that, liquid crystals, which we won't go into. But they've made use of, some companies have actually are marketing displays that are making use of the field emission, because really compact flat picture tube you can make use of to create this. And the way they do it is to make use of actual electronic processing techniques, like you make devices. So you etch suitably inside a substrate, and then you have suitable layers that are deposited. I'll try to sketch it to give an idea what it looks like. Little cavities that are etched out. Okay. Imagine this to be a sort of rounded figure. We are looking at a section of it, And there are millions of these little cavities. So in the plan view, it's simply a hole like this with a dot, or the cone coming to a tip. If you're looking from the top, what we're looking at is a cross section where we can see a cutaway, that there is an emitter tip like this that has been etched into the substrate by using electronic processing techniques. So the millions of these that are created, it's all a batch process. I'm not making them one at a time. We put a mask and suitably etch it and so on, and we get these tips. So very rapidly I can design, and I can do this over fairly large areas. Maybe that is a limitation, because right now we'll have to make it in a substrate, and if we're going to use silicon, obviously I don't have silicon substrates that are that big, but obviously I don't have to do this in silicon. I can do this in other kinds of substrates that are coated and make these tips. So this is one interesting application of this phenomenon of field emission. The other one is scanning tunneling microscopy. And I believe at least I mentioned it in passing earlier. And the inventors of this won the Nobel Prize, I think in 86 or something like that. There also the principle is very similar. I have a very fine tip of metal, atomically sharp almost, typically a tungsten wire that has been etched is used to create this fine tip. Then I have a sample, and I apply a bias between these two. Okay. And if the tip is brought close enough to the sample, by close enough we are talking now of the dimensions of atomic scale dimensions, then electrons will start flowing out from the tip into this sample using the same field emission idea, particularly if the sample is conducting. The current will be significant. And now they have options for less conducting samples, where you can also do the scanning tunneling microscopy, because there the current flow is very small, picoamps and so on, but they can actually measure these. So in any case, the idea is that by moving this tip across the surface, or alternately by moving the sample below the tip, we can do two things. One, we can maintain a constant current flowing through. I fix the current by some electronic circuitry, and the way to do that will be, because I know that the current will depend upon this height. Effectively, when I fix the current, what happens to the tip? The tip will move up and down depending on the surface topology. What do I mean by that? If the surface, I drew it a flat surface, the surface is like this, and I have my tip over here. The current flow here obviously is going to be less if I keep the height fixed here than here. Right? So as the tip comes over this area, here I'm going to get less current flow. But if I'm operating in constant current mode, what it does is to cause this tip to dip down automatically, so that I get the same current flow no matter where I am on the surface. And I can track the up and down motion of this tip. It's a very fine tip, but the way they do that is by making use of a laser. A laser beam is deflected off of the top of this tip to a detector. That's called a 4-quadrant detector. And the light that is falling off will either be deflected to one of these 4 quadrants more or less. And each of those, so we have got A, B, C, D. And both the vertical deflection as well as horizontal deflections can be determined by summing up these or subtracting various segments. That's called a 4-quadrant detector. So this up and down motion which I've got now, because I have fixed the current, will give me a measure of the topology of the surface. And with this, with suitable samples, you can actually image at atomic dimensions the surface of samples. We'll actually see an array that looks as if there are atoms. What we sort of just draw schematically, we can actually get a picture, because as it goes, imagine that these are atoms. And you're getting, it's actually the tip sample interaction that is causing this motion. And therefore we get an image of the surface. The other way they operate it is known as constant height mode also. where you fix the height. I'm not going to move, it doesn't matter, and I track the current. The current will change between this point and this point. I just keep the height fixed and move it. So the current keeps changing, and I can use that current to obtain information about the sample. And this can be done on an atomic scale. So this is another sort of application of the idea of tunneling and field emission. We now come to another topic that is related to conduction. We just mentioned it in passing here and there, but I'll take it, as I pointed, I'll take it up a little more in detail here. One of the questions that was raised the other day was about the momentum of the phonon and the energy of the phonon, and as we work through this section, I think you'll be able to grasp the difference there and compare it with that of, say, an electron or a photon. Let us begin with a simple harmonic oscillator to understand how this works. And in my classical picture of a solid, I have an atom and another atom, and it's bonded, and the way we model it is that there is some mass and there's a spring in the middle. And the atomic vibrations that are there due to energy are modeled as a spring that is coupling these two atoms as they move together. That's a simple harmonic oscillator that we have. So this is an atom, that's an atom, and there's a spring that represents the bonding between them. We have that at some finite temperature there is a vibrational motion between these, and it's effectively like stretching and compressing a spring. So we've modeled our atomic motion, the vibrations, in terms of simple stretching and compression of a spring about some mean position. And in this case, average kinetic energy, average, and average potential energy are the same. Okay? It changes between kinetic and potential, but on an average, the kinetic energy and the potential energy are the same. Now consider a 1D system of independent simple harmonic oscillator. A different representation would give me effectively this. And I'm interested in the motion of this as it's pulling against these springs as a function of x. It has a mass m. Obviously, the potential energy depends on x. And so we may write that the potential V as a function of x is given by half beta x squared for small displacements, using the idea of a spring, and we are having elastic motion back and forth. For small displacements, the potential depends on x, and so the potential depends on x, and V is equal to beta x squared. That is, V has got a parabolic shape, which we can sketch. So I'm plotting V as a function of x. That's simply the plot of the previous equation. Beta, incidentally, is the spring constant, which is a measure of the bond strength between the atoms. We are neglecting some terms over here. We are only looking at the squared term. There's a cubic term which we are neglecting in the full equation. And so effectively we have the symmetry about x is equal to 0, though my curve is a little bit skewed, but effectively it is about x is equal to 0. This is known as the harmonic approximation, the neglect of the higher order terms. And the thing to note here is that I can have any arbitrary value on this curve. I'm not limited to any discrete values. Any of these, it's a continuum. I can have any possible value of potential and thence of energy. But when we come to the quantum picture, we are now moving away from the simple classical oscillator to a quantum oscillator. We have to make modifications, because when we use Schrodinger equation, and use the V term that we have just obtained, V is equal to half beta x squared, and use that in the Schrodinger equation, what we'll have then is something like this. Where the potential term is given by half beta x squared as before. It turns out here that I can't now have arbitrary values of energy for this oscillation. We've substituted into Schrodinger equation because we make use of that to solve for quantum systems. And no longer does the energy have the ability to occupy any arbitrary value. The solution of this yields actually En is equal to n plus half h bar omega. In other words, n, which is an integer, which could be 0, 1, 2, and so on, times plus half times h bar omega. What's the lowest energy that it can have? Half h bar nu, right? So the lowest energy, that is E0, is equal to half h bar nu, or h bar omega by 2, where omega is actually the angular frequency. You would simply say frequency, but it is referring to the angular frequency. Omega by 2 pi is equal to nu. So the lowest energy is half h bar omega, and that is referred to as 0 point energy. And all other levels are simply going to be separated by h bar omega. Every time we add on one n here, I'm creating a new level. But now what I have is that instead of the continuum picture that I had here, I'm going to get discrete values that depend on the value of n. Also, omega can be expressed in terms of the beta and the m that we had in that equation as root beta by m. Okay? If you look at this equation here, we can express it in terms of root beta by m. So now my plot of omega of energy versus x is no longer going to be simple continuum curve like that, but what it will be are discrete values E0, E1, E2, E3, and so on, all separated by h bar omega. Okay? So even at when there is at the lowest energy that it can have, at 0 Kelvin, the oscillator will have an energy given by E0, which is equal to half h bar omega, which is very different from the earlier picture where we had a continuum of states. And these are all equally spaced. So every time the phonon interacts with something else and it is either absorbed or emitted, we have a change in energy of h bar omega. It's going to interact in terms of h bar omega. And we can make use of this to describe even molecules, and not just one atom like that, but molecules. So if we have chlorine, 2 chlorine atoms, so a molecule can be described in this way too, of stretching and bending, stretching vibrations and compressions. Now what we look at is how the idea of the phonon emerges from this, as we will see in a second. This quantum, this h bar omega, is very similar to the idea of photon in our electromagnetic theory. that light behaves as a wave, packets, and each of those packets has got energy of h nu, right? It's very similar here, because if you look at it, omega is equal to what? So my energy term here is also simply this. And so it is these packets of oscillation, if you will, the quantization is what is referred to as a phonon. And now what we will do is to go ahead, I don't have time to go through it all, and to show the different modes by which a linear array can, we'll start with a one-dimensional linear array, and we'll see the different modes in which atoms that are arranged in a linear array like this can vibrate. I'll just mention it today, and then we'll take it up tomorrow. I could have a wave that is propagated, what is known as a longitudinal wave, which involves the motion in this direction along the linear chain. So the atoms will move along this chain, and there will be a wave that is propagated along the direction of motion. I will also have a possibility that the atoms may vibrate this way, and what we end up with is a wave that is propagating the perpendicular to the direction of motion of the atoms. This will be called the transverse wave. You've studied this before. This is similar to sound, right? Longitudinally compressed waves. That's how sound transmits. And this is what we'll take. And then we will see how we can extend this model to the actual, to derive the different modes that are possible for a collection of n atoms in one dimension, and then later to 3 dimensions, and understand the phonons. And then what I want to do from there is to take us, how does, the whole point of introducing phonons here is to look at how that affects electrical conductivity. Because phonons also influence that. And so we'll come back and look at electrical conduction in terms of the influence that phonons play there. So we'll take that up the next time.